Okay, good morning, everybody. It's very nice to introduce the first speaker of today, Michael Hutchings from Berkeley. And he will talk about the Reeb orbits frequently intersecting a symplectic surface.
All right, thank you very much for the invitation. It's a pleasure to be here. I tried to count how many times I've come here. I'm not sure. I think this is my 10th time in Brazil, my 4th time at this conference. Anyway, it's wonderful to be here, and I'll keep coming as much as I can. Okay, so the content of my talk, it's in a preprint which you can go read on the beach. As Vincent Collin reviewed in his talk, there are various theorems about existence of periodic orbits of a Reeb vector field in a contact 3 manifold. And a lot of the theorems are true for generic contact forms. And so what I want to talk about today is some things which are true without assuming any genericity of the contact form. So the question is, so what can we say about the Reeb orbits? Without assuming that the contact form lambda is generic. Well, there are different things you can ask. Well, anyway, so for me, so Y is a closed 3 manifold. Lambda is a contact form. So lambda wedge d lambda is never 0. And the Reeb vector field R is characterized by d lambda of R equals 0 and lambda of R equals 1. Okay, and then so here's the setup. So I'm going to consider a surface in the 3 manifold. Let me make the following assumptions. So sigma is a compact oriented surface with boundary. U is an embedding except possibly on the boundary. So U restricted to the interior sigma is an embedding. And if B is a component of the boundary, I keep breaking the chalk. If B is a component of the boundary of sigma, then U of B is the image of a Reeb orbit. So the Reeb orbit is a map from a circle into Y, which is, so the derivative is the Reeb vector field. You can distinguish between simple ones where it's an embedding and multiply covered ones. So here so B could map, the degree of the map from B to the circle in Y could be bigger than 1. So it's not necessarily an embedding. And I want that the ray vector field is positively transverse to the interior sigma. So equivalently, d lambda restricted to the interior sigma is everywhere positive. So this is why I say symplectic surface in the title. So aside from the boundary, d lambda is a symplectic form on the interior of the surface. And there's one more hypothesis, which I don't want to spell it out right now. I can do it later if somebody wants to know about it. But I assume that lambda is nice near the boundary of the surface. So there's some kind of simplifying assumption in the proof. Well, there's a simplifying assumption that I need to make in order to be able to prove the theorem, and maybe it can be dropped with further work. So these are the hypotheses. And then the theorem says so under the above assumptions, so the supremum of gamma, a Reeb orbit, so this is the set of Reeb orbits, or periodic orbits of the ray vector field of gamma dot sigma. So gamma dot sigma, this is the intersection number of gamma with the surface. So if gamma is intersecting the interior of the surface, then it's just the number of intersections. Each intersection, because I assumed that R is positively transverse to the interior, each intersection algebraically counts as +1. So it's just a positive integer. Well, it could be 0 if gamma doesn't intersect sigma at all. Otherwise, it's a positive integer. Gamma is also allowed to be one of the Reeb orbits on the boundary of sigma. In that case, there's a more complicated definition. Instead of writing it down, let me just tell you informally what it means. So what you do is you start at some point near the Reeb orbit, and you follow the Reeb flow for a long time, but you start close enough to the orbit that you stay near the orbit, and you follow the Reeb orbit like k times, where k is very large. You count the number of times you've intersected the surface, and you divide by k. Then you take the limit as k goes to infinity. So that will be a positive real number, not necessarily an integer. And then I divide by the action. So this is the action of the orbit. It's also the same as the period of the orbit. So this fraction, you can think of this as the frequency of intersections of the orbit with the surface. So like how many intersections are there per amount of time? So this is the frequency. And then this is greater than or equal to the area of the surface. So as we noted, d lambda is an area form in sigma, so this is just the integral of d lambda over sigma, and then divided by the volume of y. And the volume of y is defined to be the integral over y of lambda wedge d lambda, where y is given the orientation determined by lambda wedge d lambda, so that's some positive number. So that's the theorem. So it says that there have to exist orbits that frequently intersect the surface. These orbits that exist, they could be boundary orbits, in which this has a slightly funny definition. If you assume that this inequality does not hold for any of the boundary orbits, then there have to be orbits intersecting the interior of the surface, and they have to satisfy this inequality up to subtracting epsilon. So some remarks. So first of all, this fraction that appears on the right-hand side is actually very natural. So if somebody told you that this supremum, oh, this box goes out here. If somebody told you that this supremum is greater than or equal to something, then this would be a very natural thing to guess for what that should be there. And why is that? So let's start with sigma. And sort of follow the Reeb flow. For some time t, to get a map 0, comma t. Well, let's start with the interior of the let's use the interior of the surface. Okay, so here's sigma, and I start flowing it. So I'm going to generate some kind of a tube in the surface. So if this map is an embedding, then its image has volume T times the area of the surface. Okay. So if I keep flowing, well, it can't be an embedding forever, because eventually this number will be bigger than the volume of y. So it's going to have to fail to be injective eventually. And so it cannot be injective if T is bigger. Well, anyway, if I assume that it's an embedding, then it follows that T is less than the volume of y divided by the area. So as soon as T is bigger than this, it can't be an embedding anymore. So we'll come back and intersect itself somewhere. Anyway, if it's an embedding, then the frequency of intersection of any orbit has to be at least T, right? It has to be 1 over t, because you can go for time t, and there's no way you can close up to a periodic orbit. So that what appears on the right-hand side of the theorem, that's the best upper bound you could hope for, because you can actually get situations like you can make examples in an ellipsoid where this map is injective as long as this inequality holds. And then once this inequality fails, this tube will be non-injective, although it's not at all obvious that periodic orbits are going to appear in there. Anyway, that's a motivation for the number that appears in the theorem. Yeah. Yes, that is true. So you can, if you take the, if you look at the image of the surface under the flow for all time, and you take the complement of that, and you can multiply the contact form on the complement by some very small function to shrink the volume. So yes, you can replace this volume by the volume of the image of sigma under the flow. So another remark. So Urier proved that if lambda is generic, then the Reeb orbits are equidistributed. So that in particular, that means that you can find some sequence of Reeb orbits where if you take a little neighborhood of the surface, then the amount of time that those orbits spend in the surface divided by their total period is approximately the volume of the neighborhood of the surface divided by the volume of the whole 3 manifold. And if you know that, this implies that that inequality holds. And you also get the reverse inequality. And you can find Reeb orbits that are where this frequency is getting arbitrarily close to this number. Okay. And you can also you don't really need to know all the assumptions I made about the surface, so you can weaken the hypotheses in various ways. And there's a non-trivial version of that in a paper a few years ago by Bechara, Senor, and Umberto, and Pedro. So the upshot is that if lambda is generic, then my theorem follows from known results. So the non-trivial thing that I'm claiming is that the statement holds without assuming any genericity of lambda. Okay. So are there any questions about the statements? Okay, so let me show you a non-trivial example. So this is an application to mean action and the Calabi invariant. So we start with the disk, and I take the symplectic form to have area 1. So in polar coordinates, it's 1 over pi times r dr d theta. And I take a symplectomorphism of the disk, so just an area-preserving map. And I take some number theta 0, which is a real number, and I assume that for r close to 1, the map is given in polar coordinates by phi of r comma theta equals r comma theta plus 2 pi theta 0. So the map is a rigid rotation near the boundary of the disk. And really, to write this equation, I really would only need theta 0 to be in r mod the integers, but I actually want to fix a real lift of the angle. And what I'm about to tell you as a generalization to any area-preserving diffeo of the surface with boundary under some flux hypothesis. So it's a little more complicated to state. But anyway, what I'm about to say has a generalization of surface with boundary. I'll just tell you the statement for the disk because it's easiest to state. So let beta equal 1 over 2 pi r squared d theta. So this is a primitive of omega. And then there's a unique function f on the disk, from the disk to the real numbers, such that df equals v star beta minus beta. Okay, so because phi is symplectic, this one form is closed, and since the disk doesn't have any h1, it has to be exact. So I can find f, and f is only defined up to adding a constant, and I fix the constant by requiring that f restricted to the boundary of the disk is equal to theta 0. For the more general surfaces, I need to make some flux hypothesis so that I can solve this equation. Okay, and now we define the Calabi invariant which depends on phi and my choice of theta 0 to be the integral over the disk of f with respect to the measure given by omega. And then this is it's a well-known homomorphism. You can think of it as being defined on the universal cover of the space of area-preserving diffeomorphisms of the disk. So it's a homomorphism from that group to the real numbers. So it's sort of some kind of measure of the rotation, sort of the amount of rotation of the map phi. If phi is just a rigid rotation by angle 2 pi theta 0, then this number is just theta 0. And then if gamma is a periodic orbit of phi, so that is, these are d points which are cyclically permuted by the map phi. Sorry, gamma xi. Yeah.
Why is there so much argument to say that there exists a f? How can you know that f can be chosen to be constant in the boundary?
So, well, in general you can't, but I assumed that phi is a rigid rotation near the boundary. So this right-hand side is 0 near the boundary. Okay, so if I have a periodic orbit, to find the mean action, so this is 1 over d times the sum from I equals 1 to d of f of xi. So it's the average value of f on the periodic orbit. And then the theorem, so this is a corollary of the theorem over there. So if the Calabi invariant is less than theta 0, then the infimum over gamma, a periodic orbit of phi, of this mean action is less than or equal to the Calabi invariant. So the mean action is saying, like, what's the average value of f on the periodic orbit? The Calabi invariant is saying, what is the average value of f on the whole disk? So this theorem says that at least to some extent, the Calabi invariant is seen by the periodic orbits of the map. So this theorem is stated, I proved about 10 years ago. And then there are various generalizations by various authors. If I try to list them all, I might accidentally forget some, and I don't want to do that. So I'll just refer you to my paper where I tried to give a full history of that. And that proof used a filtration on embedded contact homology by linking number with a periodic orbit, which is actually quite a lot of technology. The proof of this theorem is more low-tech, and it gives a new proof of this corollary and allows us to generalize it to any surface with boundary. So any questions about what that says? Okay, so here's how we get the corollary from the theorem. So I want to start with my map of the disk and use it to make a contact form. So you can, so first of all, so by adding an integer to theta 0, we can assume that f is everywhere positive on the disk. So in this statement, if we added some integer to theta 0, that would increase f by that integer. So the Calabi invariant increases by that integer, and the mean action of the periodic orbit also increases by that integer. So the statement of the corollary is, whether it's true or not, is invariant under adding an integer to theta 0. Okay, so I can assume that f is everywhere positive, and then we can construct a contact form lambda on the 3-sphere with an open book decomposition with various properties. So first of all, the page is diffeomorphic to the disk, and the area of this disk with respect to d lambda is equal to 1. And then the binding B, well, it's okay, maybe I should start a new page here. So the return map, why do I keep breaking the chalk? I don't know, I have to be more gentle. Okay, the return map of phi from D2 to, sorry, the return map of the Reeb flow from the interior of the disk to itself is given by phi. Okay, so you have your disk, start at some point x, you follow the Reeb flow, then you come back, hitting the disk at the point phi of x. And then you can say, all right, how long does it take to get back to the disk? So the time to flow from x to phi of x is f of x. And if B denotes the binding, which is the boundary of the disk, then the intersection number of B with the disk, as I described before, is theta 0 inverse. And finally, the Calabi invariant of phi theta 0 is equal to the volume of S3 with respect to lambda. So this is just a basic construction of, like in general, if you start with a surface with boundary and a diffeomorphism which satisfies some flux condition, and then you can find the function f, and if you assume the function f is positive, then you can make a contact form like this. So this is sort of a basic construction of a contact form starting from a surface diffeomorphism. So you just have to write down some differential forms to do that. Okay, I need to not erase that. All right, so I want to apply the theorem. So by the theorem, so the area, well, what's the area over the volume? So the area of sigma is 1, because the area of the disk is 1, and the volume is Calabi. So I get 1 over the Calabi invariant is less than or equal to the supremum of periodic orbits of lambda of the intersection number with the surface divided by the action. Okay. Now, we have to think about whether this supremum could be realized by the binding. Okay. Now, I assumed here that the Calabi invariant is less than theta 0. And I have over here that the intersection number of the binding with the disk is theta 0 inverse. And the action of the binding is 1, because that's just the area of the disk by Stokes' theorem. So by hypothesis, if I take the binding, intersect, oh, and here sigma is the disk, so I should put D2. Okay, so the intersection number of the binding with the disk divided by the action of the binding is equal to theta 0 inverse divided by 1. And by my hypothesis, that is less than 1 over the Calabi invariant. Okay, so that means that this inequality about the supremum is not realized by the binding. So it has to be realized by orbits on the interior. So I get that 1 over the Calabi invariant is less than or equal to the supremum over orbits that intersect the interior of the disk. Now, because the return map from the disk to itself is given by phi, it means that Reeb orbits intersecting the interior of the disk are equivalent to periodic orbits of the map phi. So this is the supremum over gamma, a periodic orbit of the map phi. And then what's the intersection number with the disk? Well, it's just the period of the orbit, and which I'm denoting by d. And then what's the action? Well, because the time to flow from x to phi of x is f of x, that means the total time to go around this orbit is the sum of f over all the points on the orbit, which is what I was denoting by the action of the orbit. And then if you just take the reciprocal of both sides of this inequality, you get exactly what I was supposed to prove. So that's a large family of examples where this theorem says something non-trivial. Any questions about that? Okay. All right. So now that we've stated the theorem, you say, all right, well, how are we going to prove something like this? So here's an introduction to the technology that's in the proof. Yes.
So you mentioned that in the main theorem, the reverse inequality holds in this operation.
Sorry, can you say it again more loudly?
Yes. So you mentioned that in the main theorem, you can have the reverse inequality under some genericity assumption.
Uh-huh.
And you get the reverse inequality here just from the main theorem. In the corollary.
So in general, I don't know how to get the reverse inequality for the Calabi invariant business. In the disk case, there is a paper proving that. I'm afraid I forgot exactly who the authors are, but it's in the, it's cited in my paper. For the more general surfaces, I don't know if that's true or not. It is true generically for similar equidistribution business. Okay, so the main technology is what I call elementary spectral invariance. So the input is a closed contact three-manifold. And the output is a sequence of real numbers so they start at 0. So C0 is equal to 0. C1 is positive. And then they are non-decreasing. But they are all finite. And these numbers have the following properties. So key properties. So first of all, there's spectrality. So for each k, there exists a finite set of not necessarily simple Reeb orbits such that ck of y lambda is the sum over I of the action of alpha I. So each ck is the total action of some set of Reeb orbits. And in this context, the fact that these numbers are less than, well, actually, okay. Well, anyway, this is a non-trivial statement. I mean, this implies the Weinstein conjecture in 3 dimensions. So it's not completely elementary. And then there's a C0 continuity property. So if f is a smooth function, and if f is small in the C0 norm, then ck of y e to the f lambda minus ck of y lambda is small. So you can take the contact form and multiply by any non-zero function, but if your non-zero function is close to 1, then you won't change the spectral invariant very much. And then the most non-trivial property is the Weil law. Which says that the limit as k goes to infinity of ck of y lambda squared divided by k is equal to 2 times the volume of y. So to clarify a little bit what's going on here, I should say, like, another way to say this, it's like, suppose, well, I haven't told you the definition of these things yet. So suppose anyway, when you write the definition at first, a priori these things could be infinite. And the spectrality axiom says that for each k, if ck is finite, then there exists a set of orbits. So the definition of ck, it's some kind of infimum over actions of some orbits. A priori could be infinite, like maybe there could be no orbits at all. So if you can prove that C1 is finite, then that implies the Weinstein conjecture in 3 dimensions. Now once you prove the Weil law, you get the finiteness of all of these numbers. Okay? So the Weil law is the key property which, well, a very simple corollary of the Weil law is that all these numbers are finite, but the Weil law tells you a lot more. And the proof, okay, and where does the Weil law come from? So these elementary spectral invariants, these are a simplified version of spectral invariants coming from embedded contact homology. And so there's a Weil law for the spectral invariants coming from embedded contact homology, and the ECH version of this was proved in a joint paper of myself with Dan Christopher Gardner and Vinicius. And then there's a comparison theorem between the ECH spectral invariants and the elementary ones, which allows you to use this Weil law to deduce that Weil law. So this Weil law, and the proof for this ECH Weil law uses Seiberg-Witten theory. So this is a highly non-trivial fact. In the case when y is a 3-sphere, I can give you an elementary proof of the Weil law without using any cyber-Witten theory. For general three-manifold, you need that. So this is the sort of hard part of proving anything. Anyway, so let's suppose you believe that you have spectral invariance satisfying these properties. So you go to a contact invariant shop. And you buy a box of spectral invariants. On the box it says, these spectral invariants feature, spectrality, continuity, via law. Like, it's $10. Like, all right, great. So you buy this box of invariants, and then how are you going to prove this theorem? So let me give you a sort of heuristic sketch. So the actual proof is a little bit complicated, but here's a heuristic. So it's just, so this is the rough idea of the proof of the theorem. Where's my eraser? So we consider a one-parameter family of contact forms lambda delta parameterized by delta greater than or equal to 0, with lambda 0 equals the original contact form. And what I'm going to do is increase the contact form near the surface. So lambda delta equals e to the f delta times lambda, where f delta is supported in the neighborhood of the surface. So what does that do? And f delta is going to be greater than or equal to 0. And you can set this up so that, at least away from the boundary of sigma, so there's something a little complicated that happens near the boundary of sigma, and we're just going to ignore that for this heuristic introduction to the proof. Anyway, away from sigma, a Reeb orbit gamma for lambda gives rise to a Reeb orbit gamma delta for lambda delta, such that the action of gamma delta is the action of gamma plus delta times the intersection number of gamma with sigma. So here's sigma. So I start with I start with some Reeb orbit gamma, just going through sigma, and then after I do this deformation of the contact form, well, when the orbit gets close to sigma, it's going to get deflected somehow, but then it's going to come backward to its original trajectory. But it's going to get deflected and take a little longer to cross the neighborhood of sigma. So it's like you start, there's like high winds near sigma. So you're walking along and and then the wind blows you in the other direction, and then you keep going and it's fine. Okay. I should keep the viola. And the other property is that the volume of y with respect to lambda delta is approximately the volume of phi lambda plus doing such a good job not breaking that one, and then I dropped it. Plus, I'll buy you all a box of chalk afterwards. Okay. Plus 2 delta times the area of sigma. Okay. So let's suppose we have that. And then suppose that every Reeb orbit gamma for lambda satisfies gamma dot sigma divided by the action of gamma is less than or equal to f. So f is some upper bound on the frequency. Well, so then that means that the actions of the orbits for gamma delta can't increase too much. So what you find is that this gives you an upper bound on the spectral invariance of y lambda delta divided by the spectral invariance of y lambda. So that's going to be less than or equal to e to the delta f. So because you have this continuity, so as you increase delta, the spectral invariance varies continuously, and at least generically, the derivative is given by, you just like look at the orbit and see how much its action is changing. So the derivative of the action is given by the intersection number. So you get some upper bound on how much the spectral invariants are increasing, and then you do a little calculation, and you find that if f is too small, then the spectral invariants of lambda delta are not going to grow fast enough. You're going to get a contradiction to the Weyl law. So if f is less than the area of sigma divided by the volume of y, you get a contradiction to the Weyl law. So you compare the Weyl laws for lambda and lambda delta, like the CKs for lambda delta have to grow faster because the volume's increasing. So that, and if f is too small, then that's not going to work when you compare it with that. That's the basic idea. The actual proof is kind of complicated, but hopefully that gives you an idea of what's going on. So thank you.